So beyond moving average, then there's a whole set of exponential smoothing models where we can actually apply weighted averages to the past observations to smooth out the forecast. So the first one is called simple exponential method. This is when uh, we see no specific trend or seasonality that we want to capture when we make forecast. So when we perform a simple exponential method, we're essentially performing some kind of moving average or weighted moving averages, but it's not defined by a particular span um, per se, but we define the change iteratively. So the change is determined by partially the last one, the last observation, and all the previous observations. So each forecast or each fitted value is defined by partially the last observation and all of the previous forecasts, right? And so you can see that if you keep doing that, then all of the previous forecast will depend on the previous observation, so they all somehow weigh into the next prediction and the next prediction and so on. And then there's a smoothing constant alpha that's added into that to give a weight to the immediately prior observation. So alpha is always between 0 and 1, so that gives the weight to the most recent observation or the most recent previous observation. And if we use a smaller alpha, then it means that the larger influence from distant past. And when we have more and more observations added into the next prediction, then of course the forecast is smoother. But if we use a very large alpha, let's say that when you look at this, look at this equation, and then you say that, oh, if alpha is almost 1, then basically you're predicting the next observation that's almost the same as the previous observation, right? So large alpha means influence only or mostly come from the most recent past. So a lot more sudden changes are preserved. So what alpha value should we use? Well, it's actually a very difficult thing to determine. Yeah, as said in the book, we usually start with alpha equals to 0.1 or 0.2, and then we can vary that and see if the smoothing or the forecast will give us a better description or better fit of the value. Next, when we see a trend, then we can apply the second level method called Holt's model. Basically, Holt's model preserves the simple exponential method with the alpha, but it adds a second smoothing constant beta to capture the trends. So in addition to the level, which is defined iteratively, that between with the prior observation and all the prior levels, so we have another value called the trend, basically defined in a very similar way, but the trend is the changes in the series from one period to the next. So if you see a constant change or regular change, then that is a trend, right? So if we keep going higher and higher, and the trend is always positive, then the change is always positive, then that is a trend. And the trend may actually change over time. So we also want to smooth out the trend. So trend is sort of like a second level construct above the data, the existing data. So we have a set of observations. Let's say that we have 100 observations, but we have 99 changes, right? So the changes are derived from the observation, but the changes can also be a little random over time. So we may want to smooth out the changes also. So we apply the same idea to the trends or to the changes. And beta is a similar smoothing constant if we consider how what alpha does for the actual observation. Beta is so beta does the same thing for trends. So beta gives more weight to the last change than the trend from all previous ones. So basically, we're adding the beta to describe trends on top of the alpha to describe the actual, just a simple observation. And also, so the same thing, the characteristics of alpha apply to beta also. So beta is between 0 and 1, and larger beta means that we give, so the trend is more similar to the previous change. So the changes of trend is more dramatic. So we'll see that the trend may change quickly over time. But if we actually have a smaller alpha, a smaller beta, then the trend will stay very much the same over time, because we now smooth out the trend with many different observations. So when beta is very small, then basically we're predicting that the trend will not change over time. So that's when we want to take into account the trend. But what about seasonality? Well, the seasonality can be treated with a Winters method again. So whenever we say the Winters model, we also assuming that the model already has the alpha and beta. So sometimes we call it Winters model, sometimes we call it Winters Holtz model, because whenever we have seasonality, we almost always have trends. So the Winters model, on top of the alpha and beta, we add another seasonal index to the and the corresponding smoothing constant, gamma. So gamma really controls how quickly the method reacts to the overall changes in the seasonal pattern. So higher gamma means that there are higher level of seasonal changes. Smaller gamma means that there's smaller level of seasonal changes. So seasonal changes are basically the specific performance of that, or the specific value change of that particular observation over a period of time. Of course, it's sort of like it's the season that we're looking at, right? So it's a span that describes the different seasons. So when we use the Winters method, Winters model, then we can treat both the additive, which means that seasonality can be described by an absolute changes, or multiplicative, which means that the seasonality can be described by a percentage change, or the change of the rate change. So those exponential smoothing models are probably the most commonly used models for forecasting with time series. So simple exponential Holtz and the Winter Holtz help us treat all kinds of different time series. But specific to seasonal models, there are additional ways that we can actually treat the seasonality. So one way is to deseasonalize the series. So if we take out the seasonality, then we can see the overall trend, which is great. But of course, the actual forecast has to have the seasonality added back in. So one way to do that is to separate the seasonal components from the trend. We treat them separately, and then we can draw the trend and add a seasonality back in. So this ratio to moving average method is to help us find a seasonal index for each point. So that we can separate the seasonal index from the rest of the observation, and then once we find the seasonal index, then we can divide each observation with the seasonal index. So basically take the seasonal index, take the seasonality out, and then we can forecast the series after the deseasonalization. Then we can actually forecast with the appropriate method. We can use regression, we can use Holtz, and anything like that, and then we add the seasonality back by multiplying the seasonal index back. So you may say, why do we want to do that? Why don't we just use Winter Holtz or some other methods that can treat seasonality with everything else? Well, the advantage of this is that we can actually see the seasonality separately. So we can actually draw the seasonality separately from the trends. So if you want to understand the seasonality away from the trend, and if you want to see the overall trend without a seasonality at all, then the deseasonalization is a good way for forecasting. Another method is to use the estimate seasonality with regression by introducing dummy variables. So let's say that we see the seasonality behavior of 4 seasons. So quarter one, quarter two, quarter three, and quarter four. And then we introduce 3 dummy variables. So the base case is quarter one. The first dummy variable describes quarter two. The second one describes quarter three. The fourth one describes quarter four. Then once we do that, then we get then we when we do a regression, then we actually have 4 different regression equations, right? Each one describes a seasonal. So now we can actually use 4 different time series, one for all the quarter ones, one for all the quarter twos, and one for all the quarter threes, and one for all the quarter fours. So each one will actually have that particular seasonality built in. So when you use those 4 to make forecasts, then you can actually draw out basically the combination of the changes over 4 quarters, but with separate predictions with all the seasonality built in. So this is also very commonly used when we know exactly how the seasonality will behave. Of course, this requires some prior knowledge of the seasons. So for example, the seasonality, is it quarterly, is it monthly, is it daily? So once we know that, then we can use this method. And just remember, just like in the case when we use dummy variables, so you introduce a seasonality as a categorical variable. So if there are 4 possible seasons, then you need 3 dummy variables. If there are 12 possible seasons, then you need 11, and so on and so forth. So we've learned a few really useful time series forecasting models that you can use probably immediately at work. So before we leave this topic, of course, I encourage you to practice through the examples and homeworks and so on, and so that you know how to use those methods to actually apply to the data set that you see on your job. But before we leave this topic, I want to give you some thoughts regarding the time series forecast. Whatever method you use, you should always remember that forecasting is harder when you try to make a longer range forecast. Of course, that's easy. It's easy to understand. It's easy to tell what tomorrow's weather may be versus, say, the weather of a month away, right? So the forecast is always easier if we make the near-term forecast than the longer-term forecast. But sometimes a forecasting a time series that gives us a curve that actually gives people the wrong impression that this curve will just go on forever. This is absolutely not true. So the curve that comes out of a forecasting model probably has a much stronger predictive power for the next period, or for the next 2 or 3 periods, than say for 100 periods ahead. So that's something that you always want to keep in mind. A better fit does not mean better forecast. This is best observed when we talked about noise. So we can come up with a model that actually almost track the period to period movement almost exactly. But that also means that all the noise is taken into consideration, which most of the time we don't want to. We want to smooth out the noise. But as we talked about earlier, sometimes it's really hard to separate what is noise, what is trend, what is a trend, what is seasonality, what is a cyclical behavior. So you want to use the model to somehow to see how much do you want to smooth in the forecast. You smooth out the forecast more. You smooth out the data description, the series more than you take out the noisy components. But sometimes the noisy component can be seasonal, or it can be a cyclical trend. So you have to figure out how much you want to smooth out. But if you use a method that can faithfully describe the series, that means that all the noise is being taken into account, which you certainly don't want. And then sometimes in the textbook or online, and they're advocating certain sophisticated method. Actually, in the textbook, it talked about there are other more sophisticated method like improvement over winter's halt and all that. But just remember, more sophisticated method doesn't mean better forecast. So in the case of regression, the regression itself is a holistic method. Of course, there are a lot of different aspects that we didn't study in regression, but if we study more, then we know the applicability and the limitation of regression. But here it's a little different. There are many different ways to perform time series forecast, and more mathematical operations can be added to that. But it doesn't mean that when you have a more sophisticated, more mathematically driven model, the forecast is always better. You know, that's what people always assume, but that's really not true. Finally, when you read through this chapter, you'll see that most of the models require very complicated mathematical operations. But that doesn't mean that you have to do that yourself. It's really important for you to understand the underlying model or the methodology. But once you understand that, then you can use the appropriate tools to actually perform forecast almost on a daily basis. So stat tools, for instance, is one of those tools that you use almost like just a form filling exercise if you want to make a forecast. Even with the sophisticated methods such as Winter's Hold, you just have to fill in alpha, beta, gamma, and then boom, you get your forecast, and you can actually see the curve that you draw out for the time series. So I would encourage. So don't. What I'm trying to say is that don't be discouraged by the complicated math, which is a lot, especially in this session. But you need to understand the underlying. So for instance, the what does alpha, beta, and gamma mean? But you don't have to do all the calculations yourself. You don't have to understand exactly how the math works. But once you understand all the intricacies and characteristics of a particular method, then you can just use a good tool such as stat tools and start applying these methods to the data set that you encounter at work.